strong enhancement of intensity when the system enters the antiferromagnetic phase. But the intensity enhancement occurs at where the lattice mode is dominant. Here, there's no spin wave intensity. But from the temperature dependence of the observation, it is reasonable to propose that this enhancement is actually related to what's happening in the magnetic channel. But it's hard to imagine how this magnetic excitation near Q equals pi can be mapped to a mode near Q equals 0 and interact directly with the phonon mode here. So what we think about this is if we think about the magnetic order, here is actually magnetic Bragg peak based on this cycloid order, and the polar order here, they are actually connected, associated with each other based on this DM interaction. So if you have two orders that's coupled together, if one order, say here, the spin order, starts to fluctuate, creates spin wave excitations, it is natural to assume that some certain excitation mode will also be coming out from the other order that's near Q equals 0. So that's basically our idea of how this spin wave mode can be mapped to the lattice mode. And the details of that mapping, I'm just going to go briefly through this, not really trying to get an exact mass model, but this probably will help you understand how we think about this. So here, basically, that's a spin structure in BFO. Along one-on-one direction, you have spins being antiphase. Along the perpendicular cycloid direction, O1 bar 1 direction, the spins sort of rotate from the cycloid plane. And the spins and the polarizations, they are sort of coupled through this DM interaction where Si cross Si plus 1, and then the cross product of the connecting factor of them will give a positive polarization along one-on-one direction. And we can see easily if we do that for the second row, we always get another positive polarization on the. So basically, this is mapping a antiphase spin structure, which corresponds to magnetic Bragg peak at Q equals pi, to an in-phase polar order, which corresponds to the nuclear zone center Q equals 0. So similarly, if we consider spin wave excitations, well, for classic spin wave theory, the spin wave excitations are actually spins precessing around the original direction. But in our case, we can just think about the in-plane component, because actually, if you look at the out-plane component, their effect tends to cancel out. Okay. So if you look at the spin fluctuations, basically, we can just put a simple model, put everything, the time dependence of spin vectors into this formula, and then we get a time-dependent polarization. And this term actually comes to be a static term, P0, which is the original term, plus a fluctuating term. And the fluctuating term, we can see, is actually a second-order effect. It only comes from the two spin fluctuation term. And if we think about the direction of this fluctuating term, we can see the top row, the direction of the fluctuating polar mode actually comes along the positive one-on-one direction. The bottom row, if we do this cross product, it actually also gives a positive one-on-one fluctuating term. So this is a simple scheme where one couples a antiphase spin fluctuation mode that appears near Q equals pi plus Q to a in-phase polar mode which appears near Q equals 0. So that's a simple phenomenological model that explains what happens, how one can map a spin wave mode near Q equals pi to a lattice mode near Q equals 0 through a dynamic sort of DM interaction. So what happens here is if we have a spin wave mode near Q equals pi, that can be mapped to a mode which is shown by this dashed line. This is supposed to be a pure lattice mode that's induced by the spin wave excitation near Q equals 0. So this mode, if we call it a magnetophonon mode, we try to measure it, we never see a entire mode like this near Q equals 0 in our measurement, because most likely it's a second order effect. However, if this mode, this dashed line mode, which we can sort of see on paper but not in reality, if it crosses a real polar phonon mode, and if they have the similar eigenvectors, let's say, there could be an enhancement at the crossing point, which is what we saw as the resonance. So if we calculate where the crossing point is based on the spin wave dispersion being mapped near Q equals 0, the crossing point is at energy, of course, the optical phonon energy, but at a small but finite Q, about 0.015 reciprocal latitude. So this actually naturally answers our previous two questions. First is, why do we see these modes, this spin resonance only near 111 Bragg peak? The reason is because our coupling between the between the spin fluctuation and the polar fluctuation is only strong when you couple to the 111 polarization. So you see that near 111 Bragg peak, that's sensitive to polarization fluctuation along 111 direction. The other question is, why do Raman measurements not see this enhancement? Because in our neutral measurement, we have a rather coarse Q resolution. So when we measure near Q equals 0, it actually covers this small q. But for Raman measurements, this q is actually non-zero. So it's not observable by Raman measurements. So that's basically what how we try to explain this. And the last figure I want to show is a confirmation where we look at magnetic field effect. So basically, if this model is correct, under this picture, if we are able to affect the coupling between the spin, cyclic spin structure and the polarization in any way, then it may also affect this phonon resonance. We were able to apply a big magnetic field, like 13 Tesla. And after this magnetic field is applied, the spin structure, exact spin structure, is not clearly known because it's hard to measure single crystal diffraction at this high field. But what we know is there is a huge enhancement of polarization going along 111 direction when you apply a big field like this. So what happens here, if we measure this phonon resonance under a big field, here's the magnetic Bragg peak, so showing that the magnetic structure has been affected by the field. Exactly what it is, we don't know for now. But if we measure phonons, this is measurement near 111, where the enhancement, where the phonon resonance occurs, we can see that there's also a big enhancement of this resonance intensity with field. If we go away, slightly away, go to 1.1, 1.1, 1.1, we see that enhancement is not there. So basically, all these results suggest that we are really seeing a very interesting dynamic coupling between the magnetic excitation and phonons. So the summary is here. We see an optic phonon intensity enhancement near the zone center, measured at 111 when the antiferromagnetic order is established. So this is due to a possible dynamic coupling of spin wave onto phonon mode, and also the resonance is further enhanced with large magnetic field when the ferroelectric polarization is also enhanced. Okay, thank you.
Thank you for a nice story, experimental one. Yes.
Hi, nice talk. Nice talk, thank you. So at the beginning you show some plots of the phonon vibrations, right, as a function of temperature. But so you go quite high in temperature, so you go up to 800 Kelvin or so.
700, yeah, well, we couldn't go very high.
Yeah, so my point is, so even at high temperature, you still just look into the low energy phonons. Why you do that? So I mean, when you have a large temperature, the phonons that becomes more important for the vibrational or thermodynamic properties of the systems are high energy. So it's on those that probably you could see larger effects from the magnetic disorder. So if you look into the low energy phonons, even if you go high in temperature, you wouldn't see anything there probably. but it's because they are not really coming into play.
Yeah, you're right. There are a number of reasons why we do that.
Yeah.
One is technical reason. It's hard to measure higher energy phonons.
Okay.
Second is, as I said, there are some motivations. One of the motivation of our study was this hybrid mode that Raman people have seen, and those are at lower energies.
Okay.
So partially we were looking for that, and also another motivation was we were not really looking at, say, magnetoelastic coupling that affects overall phonon structure. We are looking at more, limited to certain regions. So a number of reasons why we didn't do that. It would be hard to do that with a small crystal. So in the future, that's one of our plans, because if this model is correct, then we would possibly also see some effect at other locations at higher energy phonons.
Okay, thank you. I see.
Okay.
Thank you.
I have also a question. Did you try to calculate dynamical structure factor, the phonon intensity? Would it be like contribution of the magnetic scattering in your experiment, or just nuclear scattering for the phonon?
Well, you mean just calculate the phonon structure factor across? No, we didn't do that. But the reason we did not do that was because this enhancement, I just cannot find any reason that the enhancement would just come in at Q equals 0, but not somewhere away from that for that certain mode, right? I mean, if it's a structure factor issue, normally you would expect at least big part of the branch intensity increase. So I didn't do that. And I truly believe this enhancement itself is purely nuclear. I mean, it's induced probably by magnetic scattering, but what we see is probably purely nuclear.
Okay. Let's thank the speaker again. So in this multiferric session, we had a little bit of